Wow, there's a very detailed question in the chat.
Yeah. So maybe I'll start. I'll wait until the it's kind of time to start,
sure.
because maybe it will be of interest to others, and then
sure.
I'll answer.
Sounds good. Yeah.
So hi everyone, welcome back to this series of lectures on statistical mechanics of disordered systems. So in the last 3 weeks, we have covered quite a bit of ground, and we have first started our study with query-based models and their generalizations. And okay, there we also trained our understanding of Hamilton-Jacobi equations. And then last week, we turned to models of statistical inference. And here we saw that the techniques we developed for these query-based and generalized query-based models could also be applied. And on this point, there is a question in the chat about how to see the convexity of this free energy, which we denoted by Fn bar as a function of at least convexity in H. And so this I had mentioned last time, no, not last time, maybe 2 times ago, I had mentioned some heuristic for why this is plausible, but I had not actually given a proof. And it's true that we cannot just say, oh, it's a Laplace transform, and therefore it's clearly it's convex. This is the way we did for query-based, because in the exponential, we have the square root of H instead of H times blah, blah, blah. So if it was just H times some random variable, then we would know that things are fine. But it's not like this that the thing appears. It's with the square root of H. So yeah, so the heuristic I had proposed is that when we differentiate, what appears is this scalar product between X and X bar. And so it's plausible that as we increase H, as we increase the strength of the signal, we should be able to recover more information about X bar, which means have better alignment between X and X bar. And so it's plausible that this derivative in H is itself increasing as a function of H. Okay, but it's nice to say it's plausible. It's another thing to verify that it's true. And for this, in fact, I don't know, I mean, beyond the heuristic I said, I don't know how to do it except by just doing the calculation. And since this was, I mentioned this during the session on Thursday, I think, so it's 2 sessions ago, when we already had another relatively lengthy calculation to do. So I thought one calculation is enough for 1 session. But it's of a similar spirit. So when we differentiate again, we have some additional Gaussian integration by parts to do. And ultimately, we find that the quantity that we obtain like this is indeed non-negative. And yeah, it's not obvious, but it's written in the handwritten notes. So if you go to the Dropbox, you'll find it. I think it's around page 9 or 10, actually, of chapter 5. Right. So yeah, if there are other questions on what we have done so far, please feel free to express them. That's really a good idea. And if there are none, then let's talk about what we are going to occupy us for the current week, namely spin glasses. So spin glasses was, to a large extent, my actual motivation for all of the things we have talked about so far. But progress on this topic is not yet let's say the results I can present here are not completely mature yet. I have partial results, but yeah, there is still a lot of things to figure out here. So we'll see that some of the techniques that were relevant in these other models, well, okay, some of the techniques will also be useful here, but some others will no longer be, let's say, powerful enough to really cover what happens for spin glasses. So as a starting point, I would like to provide some brief overview of the sort of result I would like to discuss. And overall, it's about okay, first defining what are the spin glass models, and then describing without explanations or without much explanation yet the sort of result I would like to get that are supposed to describe the limit for energy. Okay. So, and this is still partly conjectural. All right, so let's start with this. So in order to keep notation not too heavy, we are going to focus on two specific models of spin glasses. So let's say we mostly focus on two specific models. The first one is called the SK for Sherrington and Kirkpatrick, SK model. So this is the one that, if you happen to remember, during our very first session, we talked about in the context of a group of people that needs to be split into two. So it looks like this. So for every sigma in Rn, we set the energy function Hn as a function of sigma, which is 1 over square root of n, sum over all I and j of jij, sigma I, sigma j, where jij are independent standard Gaussians. That's one model. This model is actually relatively well understood, and yeah. The second model that I want to discuss, on the other hand, is less understood, and I'm going to call it the bipartite model. And it's the situation in which these units, these spins sigma I, are organized on two layers, and they only, in the energy function, there is only interactions between one layer and the other layer. So formally, we can define it like this. So now I imagine that a given configuration is a pair sigma 1, sigma 2, where each coordinate is a vector of n components. We set, so for each of these guys, we set the energy function to be, so again, 1 over square root of n, sum over I and j of sigma 1 I, oops, I forgot the j, jij, sigma 1 I, sigma 2 j. Okay, so remember that the picture you should have in mind is that we have our configurations organized on two layers, and we have links between all of these layers, like this. Okay. In fact, one of the people in this collaborative LaTeX team has made a drawing of this, and And so it's much better done than what I did here in the margin. So yeah, once again, I take this opportunity to thank all the people who work on this collaborative LaTeX editing. I think they're doing a great job. So yeah, thanks a lot for this. Okay, so are the definitions clear? So we want to understand the behavior of this energy function. And in fact, more than the explicit expressions I have just written, it's better to focus on what is the covariance function for this energy. So more useful to keep track or to, yeah, see. So what are the covariance functions? So for SK, what I mean is that if you take two configurations, what do you get when you compute the correlation between this energy function at two different points? And so, if we think about doing this calculation, so it's this thing that is being multiplied by that same thing evaluated at tau instead of sigma. And the JIJs are independent and they are centered as well. So when we take the expectation, all of these, in principle, we have two of these sums. So the indices are run freely each on their own. But if we want the JIJ to have non-trivial correlation with another JIJ in the, or let's say JKL in the other sum, we have to have that the indices are the same. So the correlation that will show up here is 1 over n times sum over I and j. Instead of repeating the indices, I just have a single sum as in the original. So it will be sigma I, sigma j, tau I, tau j. Okay, and this I can rewrite as the sum over I gives me the scalar product between sigma and tau, and same for the sum over j. So this is 1 over n times sigma dot tau squared. Okay, and maybe it's actually a good practice to think of normalizing the scalar product, so that typically we think of the coordinates of the sigmas to be of order 1, so the scalar product will be of order n, and so it's perhaps cleaner to think about writing it like this. Yes, so there's a question in the chat, which is very important indeed. So for different configurations, we use the same JIJs. So the setting here is that, first of all, let's say at the beginning of our discussion, we pick this family of JIJs, and now they are here, they are fixed, and we look at this energy function. So it's really, if you think about trying to study a function in high dimensions, in some sort of typical function in high dimensions, like you're picking this function at random according to this procedure. Okay, so that's the correlation function for the SK model. And now what about the bipartite model? So for the bipartite model, you remember that each guy really comes as a pair of vectors. And really pretty much the same sort of calculation we'll show, except that we have this extra index 1 or 2 to keep track of. So what we get is sum over I and j. of sigma 1I, sigma 2j, tau 1I, tau 2j. And so we can, rewrite this in terms of scalar products as before, but notice that to be the scalar product between the first components of sigma and tau multiplied by the scalar product of the second components of sigma and tau. So this time we get, let's say, n sigma 1 dot tau 1 divided by n sigma 2 dot tau 2 divided by n. Okay, and these are the functions that will be, so here we have the square function, and here we have the product function. These are the functions that will really, show prominently in our analysis of the problem. So I said I won't focus on these two models, but just so that you have some idea of what class of models we can actually talk about, let me mention what this class is. So in general, all considerations here in this chapter apply as well to the following marginal model. Okay, I wrote general twice. So yes, the marginal model is that you can imagine that your configuration sigma is a vector of a finite number of types. So for bipartite, there are two types, sigma 1 and sigma 2. But maybe you could imagine there are D types, and we keep D fixed, 2, 3, 5, but not diverging with n. So there are D types, and for in the bipartite case, each of these coordinates belongs to R to the n. But in general, you can imagine it's an arbitrary Hilbert space. So you can take this as being in some Hilbert space. I'm going to denote script h like this. So D is an integer, is fixed. Hn is a Hilbert space. And you can think of this as being Rn. Sometimes it's convenient to allow for somewhat marginal spaces. And then the next requirement I'm going to place here is something that says that the model is mean-field in some sense. And the way I'm going to capture it is that I'm going to ask that the covariance function, the thing that we computed here, for instance, is always a function of the matrix of scalar products, like it was in this case. So let me write this. And so for some function, let's say smooth, just for simplicity. Which I'm going to denote psi. So it's going to take as an argument this matrix of scalar products and return a real number. We would want that. So for every sigma and tau in this product space, we will want that the correlation is n times this function psi of the matrix of scalar products. Okay, so in the for SK, so for SK and for the bipartite models, the Hilbert space is just Rn. For SK, D is 1, and Xi is the square function. For the bipartite, D is 2, and Xi is the product of the diagonal entries. Okay. So in general, you see that there's some matrix that may be involved, but it's nice that we don't have to worry too much about matrices, even for the bipartite case, which is convenient. Okay, and the function psi is really what is most useful to keep track of, as I mentioned earlier. In fact, this is the function that will show up in the expression of the Hamilton-Jacobi equation that I want to shoot for. So the function psi is what shows up, which was in the relevant Hamilton-Jacobi equation. Okay, this is just a remark for the future. Okay, so that was a short digression on these more general models. But as I said, I think from now on, I will essentially always talk only about SK or bipartite. And like for the models we have studied so far, Curie Weiss or generalized Curie Weiss or statistical inference, we can also choose a reference measure. So it's this thing that we denoted by Pn most of the time. And again, for simplicity, I'm going to assume something simple for Pn. So we also have to So this part is really only for notational simplicity. It's just we slightly shorten some expressions. For convenience, we assume the following. So I'm going to assume that the sigma, for the reference measure, the sigma is, so it's IID coordinates, and each coordinate is either +1 or -1. So Pn is a product of n-fold tensor product of the single measure with P1 supported on ±1. So this is for SK. So you remember, okay, or you may not remember, it was a long time ago. In the first session, when I discussed the SK model, I was doing this sum over sigma in the set +1, -1. This corresponds to choosing P1 to be the symmetric measure on +1, -1. Like probability to be +1 is a half, and probability to be -1 is a half. But you don't need to choose this particular balance case. And in the bipartite case, similar assumption. So in this case, I have to, there are two components. So I'm going to say that each of the components is IID according to a measure. And also the two components are independent. So again, if you wish, you can think that we're just summing over sigma 1 and sigma 2 being vectors of +1, -1. And this corresponds to choosing pi1 and pi2 to be Bernoulli 1/2 on each of the +1, -1. Okay, and now we have all of the ingredients necessary to define a free energy. So we want to to study the following free energy. So we construct it as usual, 1 over n, the log of the integral of the exponential of the energy function. And Hn of sigma is a Gaussian, so as with statistical inference, I'm going to enjoy rescaling it by square root of t. Okay, and I put a 2 for aesthetics, but that's not important. Okay, and it's pleasant to introduce a counter term, this nt, which I'm going to explain in a second. Okay, so I want to study this quantity. So in general, this n here, in general, you should write the expectation of Hn of sigma squared. But since I assume that all of the +1, -1, sorry, all of the coordinates are either +1 or -1, in the models we talk about, we always have that. So for SK, we always have that sigma squared is equal to n with this choice of measure. Okay. And with this choice of measure for the bipartite, we always have that sigma 1 squared is n and sigma 2 squared is n. And because of this, if you look at how we compute the expectation of Hn sigma squared, so let me display it. See, if here I set sigma equals to tau, what's inside the square here is the norm of sigma squared divided by n, so I just get n. Okay. But okay, in general, you could just write this expectation, blah, 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 and okay, and then I would have to explain how to remove it, and it's just slightly more annoying. But all of what I'm going to say would also be valid if you write this instead. Okay, but I don't want to bother with this. So we're just going to focus on this. Okay, and perhaps one motivation for setting it up like this is that that's a small remark, but if we take the average of this exponential, then this is equal to 1. Okay, this is in fact the calculation I mentioned when I discussed Ito calculus without Ito. Okay, it's like you have exponential of some Gaussian minus a half of the variance of this Gaussian. So this is always equal to 1. And maybe it kind of makes sense if you want to think that way. When you flow, if this I would really rewrite as some Born motion, then as you flow t, you could think of this as being a martingale. So since we want to make t flow, that's perhaps a good idea to do that. Now we're not going to put the expectation inside the integral. Okay, so the quantity that is above, quantity here is not trivial, but by Jensen's inequality, if you take the expectation outside, like if I write E here, then by Jensen's inequality, I will see that the quantity is non-positive. Okay, because log is concave, so the result will be lower than if I put the expectation inside the log. And so given that, yes, the expectation here is with respect to J. Or if we want to, yeah, so the randomness hidden inside the Hn of sigma. Yes, thanks for the question. So this E with a double bar, I always think of as being expectation with respect to the J. And sigma is the variable of integration. Okay, so if you want you don't like the integral symbol, you can think it's sum over sigma of blah blah blah. Yes, as someone is pointing out in the chat. Thanks. Okay, so by Jensen, yes. So so anyway, if you take the expectation is negative, so it will be kind of nicer if I put a minus sign in front of this quantity. It is nicer to put a minus. Oh, maybe I'll put an expectation. Okay, so let's talk about this quantity. So this by Jensen, it's non-positive. Okay, because of the remark that is below, in front of this. Okay, again, this is just for aesthetics basically, but at least the quantity is non-negative, and we'll see that it's also non-decreasing, and the partial differential equation looks nicer this way. But okay, just be aware that some things may look a little bit backwards because I will tend to put a minus sign in front of this free energy. Okay, and I think by now it starts to be clear, but it's nice to see the free energy, because when we differentiate with respect to t, we will learn information about the associated Gibbs measure. And maybe this is what we really want to understand, the Gibbs measure associated with this energy function. And maybe, as a simpler discussion, maybe you want to understand the extreme points of this energy function. And this will be captured by this Gibbs measure for very large t. When this parameter t in this integral becomes very large. Okay, so are there questions so far? So as we stand here, we have this free energy, and it's a function of t. And as we have done during the past 3 weeks, I want to carry this program of trying to discover a partial differential equation satisfied by this object, at least approximately as long as n is finite. And it's a bit like when we started with statistical inference. If we only have this t parameter, we can differentiate with respect to t to our Haas content. We will not identify a closed equation for this object. So we already saw some of this with statistical inference. We had to think a little bit, what is the right way to enrich the model so that then we can close the equation in some sense, find relationships between derivatives with respect to different parameters. And we had to also be mindful that we don't want to introduce something that looks too complicated, because otherwise, it was nice for us that when we say t equals 0, we can compute the free energy explicitly even for finite n. Okay, and so here we have to ask ourselves the same question: what sort of quantity will it make sense to add to this energy so that we can feel more optimistic that there will be relationships between the derivatives? And I'm going to actually make a proposal here and then try to justify why the proposal is reasonable. Yeah, and yes, okay, so perhaps one way to have some intuition for what to do is yeah, okay. I'm hesitating to so maybe I could try to I'll write it down, and you can scream if you find this unreasonable, but I think it's a reasonable guess. So okay, so we need to enrich the free energy, the energy. discover a partial differential equation. And as a, let's say as a first guess, we can try with the following thing. So let's say first for SK. So Fn of T and H. So I put a minus in front, 1 over n log. We could try to add a random magnetic field. So a square root of 2h, let's say z dot sigma. And then, okay, I always keep this kind of balancing term, minus nh, dpn of sigma. Okay, where z is a vector, it's an n-dimensional vector of independent standard gases. And they are independent of the other source of randomness. So they are independent of the J's. Okay, so just to echo the question that was asked earlier in the chat. So here, we pick the J's and the Z's, and then we compute this function. Okay, and then maybe after we have taken the integral, the log, then maybe we will be interested in taking the expectation, but only at the very last move. Okay, so it's best to think of these J's and the Z's as being frozen. So I think it's reasonable, especially in light of what we have done with statistical inference, because if you remember what really appears in the exponential in statistical inference, there was this term. So okay, in the notation of last week, it was sum of wij xi xj, and then we had added this sum of zi xi. Okay, so it's kind of the same construct, and also it has to kind of look a little bit like what happens inside the Hn of sigma, except simpler. So there were, okay, physicists would say two-body interactions. There was this product sigma I, sigma j, and we're kind of trying with a similar thing, but without this two-body thing. So one-body interaction, something which is nicely like a sum of things without products. Okay, so yeah, I think it's a plausible guess. And I'm going to denote Fn bar, the expectation of this quantity. And we write, oops. It's also a function of T and H. Yeah, so I think there's a question in the chat about why make the so H here the H is a constant. Okay, I mean it's a parameter that is fixed outside. So I should say like for statistical inference, it's like T and H are just non-negative parameters, and we just insert this. But I guess the question is like, why do we bother to put something random here? Why not just do like in Covariance and use, yeah, sorry that I kind of played the fool a little bit. Yeah, why don't we just do as in Covariance and just write H times the mean magnetization. So it would be H times a vector full of ones dotted against sigma if we want to use the scalar product notation. And I think heuristically, at least, the reason is that it has to be something that kind of looks a little bit like what's going on inside the HN of sigma. And because, ultimately what we want to say is that variations in T can be compensated by some variation in H here. And so, maybe locally, it's like each spin is subject to the random influence of the other spins as displayed inside this sum of Jij, sigma, sigma j. And as you slide T, maybe locally, it's as if you're kind of compensating by some random field, right? I think there's some plausibility to this. And perhaps the best explanation is to, like, the most convincing, yes. I mean, in some sense, so in the chat, someone mentions interpolation, and it's kind of similar to interpolation. The partial differential equation we are trying to find relates to finding an interpolation path. Okay, except that for the bipartite model, I think it's more tractable. Like I think it's basically the only the partial differential equation is, I think, the only way to really think about it reasonably. But whenever interpolation is possible, there is a very direct link between the two. Okay, in fact, these interpolation paths are the characteristics of the equation, as far as I understand. Okay, so I close the parentheses. Yes, ultimately, I think the best confirmation that this is a plausible first guess is to try to see what happens when we actually compute these derivatives and see if they look at least kind of plausibly related. And then you could test what happens if I do with a random field or with a non-random field and compare the plausibility of saying that there is a relationship between the derivatives. And so in order to compute these derivatives, we will have to do a Gaussian integration by parts, like what we have done last week. So let me state a result in this spirit, like describing what happens when we do Gaussian integration by parts. It's a variant of the lemma we had discussed last week about the same topic, about Gaussian integration by parts. So let me just write it down. So I'm going to state it like this. I'm going to state it in some abstract context. I think it's convenient to think of it that way. So let sigma be a finite set. And it's also as it appears in the problem set number 11. So if you look into this, you will see this exact same lemma as I'm writing here. So let's give ourselves a centered Gaussian field indexed by sigma with two coordinates, x of sigma, y of sigma. And for every sigma and sigma prime, so I choose the finite set so that I don't need to worry about measurability issues, but it's not a significant consideration. For every sigma and sigma prime, let's define this covariance between x and y at sigma and sigma prime. I'm going to denote it by C of sigma, sigma prime. So it's the expectation of f of x of sigma, y of sigma prime. It's going to be useful because as in the lemma of last week about Gaussian integration by parts, when we do this Gaussian integration by parts, we will see covariances appear. Okay, so remember there was this x minus x prime, and we have something similar here. Okay, so what do we need on top of this? We need this reference measure to define the GIST measure. So let's call it P. And now define the GIST measure. So it's the GIST measure with respect to the energy Y and this reference measure P. So here is going to be, so I use integral sign, but it's actually a finite sum. F of sigma exponential of Y of sigma dp of sigma divided by the integral of exp of y of sigma dp of sigma. Okay, so we have all our ingredients. There is a GIST measure, and there is an extra Gaussian field x, and I want to know the. So what I want to know is the expectation of this field. So okay, so there are two layers of randomness here, and it's kind of we have to keep track of each. But maybe it's best to think of this bracket as being notation for this ratio. Okay. So we have x and y, they are just Gaussian fields, and we're trying to compute the expectation with respect to x and y of, let's say, the integral of x of sigma exponential blah, 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 divided by exponential blah, blah, blah. And the claim is that this expectation, you can compute it, like it's equal to, oops, mistake, the covariance between sigma and sigma itself minus the covariance between sigma and sigma prime, an independent copy of sigma. A replica, as it's called. Well. Okay, and I claim that the proof is very similar to the one we have done last week when we were dealing with statistical inference. And it's also, so let's say proof, it's also part of the problem set. So I'm not going to explain it in great detail here. Okay, so I'm going to use this statement to compute the derivatives of our free energy Fn bar, which is written here, the expectation of the quantity on top. Okay. Other questions? Maybe it's a good time for a break. And yeah, I'm always happy to have questions also during the break. Just, I'll back in 1 minute. So why is it an integration by parts? So it's like last week, there's something special about these Gaussians, which is that if G is a standard Gaussian, then the expectation, and F is just some function, let's say smooth. And when you do expectation of G, F of G, this is the same as expectation of F prime of G. Yeah, this is true because if you write explicitly the integral, then you do integration by parts against the density of the Gaussian. And this is what you use to prove this result. Okay, so you have to, like, it's kind of encoding this property. And I claim it's, this is what I call the Ito calculus without Ito. Like actually, you're doing some version of Ito calculus when you do this. We're going to apply the lemma right away, so you see an example. So yeah, indeed, so there's a question about can we add some correlations between the JIJs? So in the two models I said they are independent and analytically distributed, but yes, you can definitely put correlations. So then the techniques I'm going to describe, the settings in which you can have a hope to find a partial differential equation essentially require that the model is mean-field in some sense. So you're free to define a spin glass on a lattice and to put the JIJs according to a Gaussian free field, but that's going to be very difficult to analyze. In the lattice, we don't know very much, even when the coefficients are IID. So so yeah, so you can, for instance, what you could do is say, okay, yeah. So for instance, instead of saying that what I want to make sure of is that at the end of the day, when you write the covariance is going to have this form. It's going to be a function of the matrix of scalar products. So I guess if you say that, so for instance, in the bipartite case, you could add interaction between sigma 1 and itself, and you could decide that it has that this random interaction has some correlation with the one that dictates the interaction between sigma 1 and sigma 2. I think maybe you want to keep things being independent as you vary I and j, but you could say that the interaction between sigma 1i and sigma 1j is correlated with sigma 1i and sigma 2j. And then you would get a model like this, for instance, I think. Yeah, I've written this down somewhere more keenly in the paper called Free Energy Upper Bound for Vectors. Yeah, I forgot exactly the title. But there I explored this more general setting, and the last section gives lots of examples, including those with correlations. All right, so yeah, let's see how to use this lemma. Okay, so this is the free energy, and this is what I would like to try to differentiate in T and in H. And maybe it's nicer to start with H. It's a little bit less, it's a little bit more explicit. So, okay, I'm going to differentiate with respect to H. H appears here, and okay, this second slot is very easy to differentiate. So mostly I'm concerned about this. So when we differentiate, as usual, we're going to get something under the GIST measure. And this something will be 1 over square root of 2h z dot sigma. Let me write this down. Okay, so there's a minus 1 over n in front. And then it's the expectation of the brackets of 1 over square root of 2h z dot sigma. And then there's the minus n, which is just okay. So yeah, perhaps one thing I should have said in the lemma is that I stated it saying x and y are centered, but if y is not centered, this is really not a problem because you can just absorb it into the definition of the measure. You could just move the mean value into some density for the measure. So in fact, whether or not what is inside the exponential is centered or not is not important. Okay, so we can just ignore the mean value, let's say. So okay, in our context, so I want to do this Gaussian integration by parts on this guy because this z is still this Gaussian thing. So this will be my x of sigma. Okay, x of sigma is z dot sigma. And the y of sigma is going to be just the expression for the energy function. So I have to compute the correlation between these two things taken at two different configurations. And in the energy, the only thing that is correlated with z is z itself. So the relevant calculation is, this is the x, and in the z, in the y, there are different terms, but only the one that contains z is relevant. So this is the correlation, this c of sigma and sigma prime that I have to compute. And this is just the scalar product between sigma and sigma prime. Okay. And right, and inside the energy function, there's also a square root of 2h. So in fact, c of sigma sigma prime is square root of 2h times this thing. Okay. So we apply the lemma. And we get minus 1 over n expectation of, so sigma dot sigma minus sigma, sigma dot sigma prime. Anyway, the result of the lemma is displayed on the top of the screen right now. You see I have this c of sigma sigma minus c of sigma sigma prime minus n. Okay, and in our assumptions, the sigma square is always equal to n. So in fact, and these two guys cancel out, and what remains is just sigma dot sigma prime. Okay, so this I get equals expectation of the bracket of sigma dot sigma prime divided by n. Okay, and just maybe I was a bit too quick with using this notation. So let me clarify the notation. This bracket here is the Gibbs measure with respect to our energy function. Okay, so this is shorthand for integral of whatever we put in the brackets times exponential or square root of 2t, hn of sigma, minus nt, plus square root of 2h, z dot sigma minus nh dpn of sigma. Okay. Yeah, okay, all this divided by the integral of the exponential of the thing. Okay, so it's the associated Gibbs measure. And the sigma prime is an independent copy of sigma under this measure, a replica. Is this clear or is this confusing? It's the same notation we have also used in statistical inference. Okay, so here we have the first occurrence of an object that is often called the overlap between two replicas, if we want to use the language. So overlap means scalar product. Replicas mean these two independent copies under the Gibbs measure, sigma and sigma prime. Okay, so yeah, let me just indicate it because sometimes I may use this language. We can call it the overlap between sigma and sigma prime. Okay, so that's the derivative in H. Now, what about the derivative in T? So the dt Fn bar. Okay, so I'm not going to redisplay it. Okay, it's kind of hidden in the very tiny script here. When we differentiate in T, what we get is 1 over square root of 2t, Hn of sigma. Let me put this, 1 over square root of 2t, Hn of sigma. And then there's this minus nt that is floating around, so we will get minus n. Okay, and so we're going to do the same, we're going to apply the lemma of Gaussian integration by parts. So there will be, so we're again going to wonder about the correlations between this field and the energy function. And in this case, the only thing that is correlated with Hn of sigma in the energy function is Hn of sigma itself. So the relevant C of sigma sigma prime is the correlation between Hn of sigma and Hn of sigma prime, which okay, we denoted by Xi in general, but is it's basically the scalar product between two configurations when it's about SK. So okay, it's and it's squared. So so let me write. So for the SK model, we will get the norm of sigma. The norm of sigma. Sorry, I had a little pause because so C of, let me write explicitly in the margin. So C of, in this context, C of sigma and sigma prime will be square root of 2t n times sigma dot sigma prime over n squared. This is for SK. Okay. So then I compute C of sigma sigma, it gives me n, and then it cancels with the minus n. And then what remains is sigma dot sigma prime over n squared. So I get And for the bipartite case, what we get instead is this thing that involves the product of the scalar products. So maybe expectation of, in general, is this xi function. Oh yes, and I should have said yes. So so I did a calculation for the t derivative for the bipartite, but I should modify a little bit this enrichment in the case of the bipartite model. Yes, so this is for SK. So okay, let's just think that it's for SK this calculation. Because for the bipartite model, it would make sense to be allowed to act differentially. I mean individually on the sigma 1 and the sigma 2. So this, I said, this is the case for SK, and for the bipartite. For the bipartite case, I would like to have, in fact, two variables with which to play. I would like, let's say, fn of t h1 h2 equals 1 over n log integral exponential da da da. Same thing as above so far. But then I will use, one of the, I want to put some random field on this first vector of n components called sigma 1, and also another one on sigma 2. Okay, I don't assume any symmetry between the two copies. The measures could have, maybe the first component has a bias and the other one not, for instance. So there is no reason we should always want to apply this random field at the same strength in the two layers. So I want to just decouple the two. So I have H1 and H2 in the bipartite case. Okay, and now and Z1 and Z2 are again vectors of n independent standard Gaussians, and they are independent of each other. They are independent of the energy of the Hn. Okay, so this was for SK, but for H1, I will get the same result, except I will get the scalar products with sigma 1 here. Okay, so let me write it down below. So for the bipartite, we will have the H1 Fn bar equals and same with H2. Okay, so let's go back to SK. So yeah, I think the ultimate explanation for why it was actually a pretty good guess to do this enrichment is that the t derivative and the h derivative look like they want to relate to one another. Okay, so observe that the t derivative is the expectation of the square of the overlap, and the h derivative is the expectation of the overlap. So if we assume that the overlap doesn't have too much fluctuations, then we get a relationship between the two, and we will get that the derivative in t is the square of the derivative in h. In fact, again, the same equation as for Curie-Weiss and as for the model of statistical inference we have studied. So for SK, this suggests to consider the Hamilton-Jacobi equation. Maybe I should write. Yeah, let me erase. We get so I'm going to write variance, and here variance means with respect to both the brackets, the Gibbs measure, and this double bar expectation. Okay, so in fact, this is again very similar to Curie-Weiss and statistical inference. And for the bipartite model instead, so this is what we get when we differentiate with respect to t, and below are what we get when we differentiate with respect to h1 and h2. So if we believe that these overlaps do not fluctuate too much, that they are concentrated, then what we will get is that the t derivative is approximately the product of the h1 and h2 derivatives. Like this. So dt fn bar minus dh1 fn bar dh2 fn bar equals, and I'm going to rewrite it like this. I'm going to emphasize that it's a covariance. Okay, so if I use observe that product of two numbers is always smaller than 1/2 of the sum of the squares. So if I use this for on this expression, what I get is that this difference between the derivatives is bounded by 1/2 of the variance of the first overlap plus 1/2 of the variance of the second overlap. Okay, so again, a situation that feels very similar to what we have encountered so far in other models. Okay, and more generally, so okay, this is if you think about these general models with the psi, you would get dtf minus psi of grad f, which looks okay. I should say with the fn bar. dt fn bar minus psi of grad of fn bar looks kind of, I don't know, something with variances. So yeah, I synchronized I was postponing reading the question in the chat, but it matches what I was talking about. So in general, it does not need to be a quadratic function. It's going to always be this function which describes the covariance. And in fact, even when you have a single component, this function psi can be something other than quadratic. All right, so what are, how do we orient ourselves in this space of models? Why do I want to single out SK and bipartite? And so the critical difference between the two models, so is that I take each as a representative of a particular class, and for SK, it represents the class for which this function psi is convex. So here it's the square function, so it's a convex function. And we know that we can write the Hopflax formula, and so in particular, okay, at least if we believe that this is the correct equation, we will have a variational representation for the free energy in the SK model and other models which have a convex function psi. Now, for the bipartite model, the function is just you take two numbers and you multiply them. This is not a convex function. Okay, and so I take the bipartite model as representative of the class of models for which the function psi is not convex. And in fact, okay, so this here I'm getting a little bit into the weeds, but just maybe for the specialists, what really matters is whether the function psi is convex, but not on the entire space where it's defined. So in the general model, this function psi takes as input a matrix, a D by D matrix. And in fact, what's really relevant is that psi is convex on the set of positive semi-definite matrices. So if you deal with a scalar model, then this just means that you want psi to be convex on the positive half-line. So for instance, if psi is the cube function, then it's convex, okay, because it's convex on the positive half-line. So in fact, for scalar models, all of the so-called p-spin models are examples for which psi is convex, okay, because it's convex on the positive half-line. And the reason is that we can do this is that these derivatives, they are always non-negative. If you remember, we've seen this in statistical inference, and this is also true in this case, because it's the scalar product between two copies. This is always non-negative. So the relevant criterion is whether the non-unity is convex on the positive half-line. So if you want to have an example where it's not convex, in fact, you have to use a model with at least two components, so hence the bipartite model. Okay, and okay, so that's one thing I wanted to talk about, and indeed, we understand relatively well the models for which the function psi is convex, and we understand relatively poorly those models, like the bipartite case, for which the function psi is not convex. Okay, so now there are very important differences between all of these models, SK, bipartite, and others. All of those spin glass models are they differ in fundamental ways with the models that we have studied in the past weeks. So there are two main differences. Okay, so yeah, the first one is that these functions are neither convex nor concave. And we started with the discussion at the beginning of today's session from the chat about how do we prove that this thing is convex in the statistical inference case. And indeed, it is not obvious, and we need to check this carefully. And in this case, actually, it just fails to be valid because of all of these square roots that are moving around in the energy function. So in the exercise 3 of the problem set 11, I propose a way to verify that really, indeed, this function is neither convex nor concave. Oh, I wrote neither convex nor convex. That's sweet. All right. Nor concave. And so in particular, our strategy based on the convex selection principle is not applicable because these functions are neither convex nor concave. So that's our main tool, let's say, is broken. And the second problem is that, in fact, these variances that are on the right-hand side are not small. Okay, I write etc. by meaning in the bipartite case, you take sigma 1 dot sigma 1 prime, etc. These things are not small when t becomes large. So in fact, you can show, at least by a perturbative argument, that this variance is indeed small for t sufficiently small. So for t sufficiently small, you can actually use this discussion and show that the limit free energy will be described by the partial differential equation we think about. But as soon as, after a point, you increase t, and then, well, okay, first of all, your ability to prove that the variance is small breaks down. But in fact, at some point, it also becomes false that this variance is small. And so what do we do next? We have something in the equation that is still not small. So it means we have actually not managed to really close the equation to find a relationship between the derivatives that asymptotically becomes exact. And so what this means is that we have to go back to our drawing board and think again about how to do this enrichment of the free energy. We have to provide with something richer in the exponential so that we have a better chance to actually find an equation that becomes valid as we send n to infinity. So we need to refine our enrichment. So yeah, we're going to spend quite some time exploring how to do this precisely, and this is really based on a lot of accumulated wisdom about how these models behave. And yeah, hopefully we will progressively develop some intuition about this, but it is definitely not an idea that you can just guess in one sentence. Like it comes with a lot of let's say prior growth of the heuristic understanding of what is going on. But just I think it's kind of interesting to at least know how formally the limit equation looks like. So when you do this guess, pretending that these overlaps are concentrated, you start to single out some equations that look reasonable, and maybe they are good if these variances are small. And in fact, the true equations are, you can formally obtain them by substituting all of the variables that show up by probability measures. So this will occupy us for quite a bit of time, but the way we're going to enrich let's say for SK, the way we're going to enrich the free energy, the energy function is going to be convenient to encode it by a probability measure instead of this single parameter H. And so then we have a free energy which depends on T and some probability measure. And let's call it mu. And then the equation that ultimately is valid is exactly the same, except you have replaced H by mu in the following way. So, so this enrichment will be encoded by probability measures. So for SK, you substitute H by, maybe I should not write an arrow, but like you just replace it by one measure, let's say mu in, so it's a probability measure on the positive half-line or non-negative half-line. And for the bipartite, you substitute H1 and H2 by two probability measures likewise. And then the relevant equation. So for SK, it will look like this. So okay, so maybe it's not super clear what it means exactly, but it's something that differentiates with respect to the measure, and then you can think of this as being just a very, very large vector which measures all of these small derivations you can do with respect to points on the support of mu, and then you sum it up all. Okay, we're going to explain this more later, but just so that you have some. I said this was overview today, so I like to at least display this formula. Okay, I see question in the chat. Okay, for the measure, this probability measure. It's more like, okay, so what is this probability measure doing? It's more like what we want to do. So we had this random field, square root of 2h times z dotting sigma in our naive guess. And in fact, we would want to make a more sophisticated guess, or at least proposal for this random field. And we would want this random field, so this will talk to you, but maybe not to everyone, to have some the structure of a probability cascade. Okay? And this probability cascade will be encoded by the measure. And this, if you think that the measure is just a sum of Diracs, this is what you get when you move around each of the Diracs a little bit. Okay, so if you think that the function, instead of being a function of a general measure, imagine it's a function of Diracs of whose height you have fixed, and so you just think of them as a function of the position of the Dirac, and then it's just the gradient with respect to this position. Okay, and then if there are lots of positions, you have a very, very large gradient, and then you take the norm, you square it. That's this quantity. Okay, and for bipartite, it's going to also look very much like some mirror image of the product of derivatives, except now we have two probability measures, and we do this product like this. Okay, and then I have to explain exactly what the integral means, but okay. It's just to give you a flavor of what it looks like. Okay, and for me, I want to display it because I think it kind of helps to visualize what are the technical difficulties and how does it relate to the standard PIMS formula. So this is an equation that has a convex nonlinearity. Think of this as being just a big gradient of which we take the norm and square. And so we know that the Hoflachs formula provides us with a variational representation for the solution. And in fact, up to a modest change of variables, this variational formula is the way the PIMS formula is usually presented. So if you want to bridge what I'm saying now with normal writing of PIMS formula, the route is through the Hoflachs formula. On the other hand, here, well, the nonlinearity in the equation is not convex, as we have said several times. And so you cannot apply the Hoflachs formula. And also, I mentioned at some point that even before we do this measure thing, blah, 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 the function is not convex and it's not concave. So you cannot either rely on the Hopf formula. Okay, so you could have hoped to also discover a variational formula using the Hopf representation, but it also breaks down. Okay, so at present, I don't know how to prove that for the bipartite model, the limit for energy solves this equation. But at least I can phrase a conjecture. Okay, I can say, okay, what I want to prove is that the limit for energy is the solution of this equation. And I can prove one bound and also some partial results in the other direction. And as far as I know, this is the only, I mean, I don't know of another way to state the conjecture, to state a plausible candidate for being the limit of the free energy in the bipartite case. All right, so I guess it's a nice place to stop. Thanks a lot for your attention. And as always, I'm very happy to take questions. Yeah, perhaps one thing I could add is in this extension where we replace H by mu, we can recover the original, quote unquote, naive guess for the free energy is the case when mu is the Dirac at the position. Okay, this allows us to go back to what the naive guess is doing. And in particular, when we set H equals 0, so when mu is delta 0 is when in the energy function there is just the vanilla Hn of sigma and nothing more. Okay, and for the bipartite is when mu1 is delta H1 and mu2 is delta H2. Yeah, so there's a question about what is the intuition for replacing H by a probability measure. This is what I was, at least it's related to what I was saying is a difficult thing to explain in 2 sentences. You have to kind of have a plausible guess for what the Gibbs measure is doing, and then try to do something with this random magnetic field, this square root of 2h times z, which looks like it, so that it can when we slide the t a little bit, you can match these variations with some variation in this more complex field, and then it's some so there will be lots of parameters to encode this more refined magnetic field. And okay, for some reason, it's convenient to encode it by probability measure, but like this is not maybe the most fundamental part. The most fundamental part is what do we write down instead of this naive random field? What is a good replacement for it? Okay, so there's a question